In this lecture, we're going to be looking at travelling waves. We'll start by looking at different types of waves, and then we'll derive an equation to describe wave motion. This lecture covers section 16.1 of your textbook. First of all, a quick recap of the most important ideas from last lecture. We saw that the projection of an object undergoing constant circular motion onto the x or the y axis undergoes simple harmonic motion. We also said that a simple pendulum undergoes periodic simple harmonic motion and that it obeys the equation. The period for the pendulum is equal to 2 pi times the square root of L on G. More complicated physical pendulums also undergo periodic motion, and they obey the equation the period is equal to 2 pi I over mgd, where I is the moment of inertia about the pivot point, d is the distance between the pivot point and the centre of mass, and m is the mass of the body. Last lecture we said that in reality simple harmonic motion is usually damped. The damping comes about typically because of forces such as friction and air resistance. It can be underdamped, in which case it oscillates, but the magnitudes of the oscillations decreases with time, or it can be critically damped, in which case this cos omega t term becomes just a constant number 1, as omega t plus phi is 0, and in which case it no longer oscillates, or we can even overdamp it, provide even more damping, in which case there's still no oscillations. We also said that we could drive a system. If we apply a periodic force, then we can cause a system to undergo resonance. So we just said last lecture that the amplitude is related to the driving force and the natural frequency through this formula. And if there's very little damping and the driving force is very similar to the natural frequency, the frequency at which the system likes to vibrate, then the amplitude of the oscillations can be very large, and this is called resonance. So this graph just shows this relationship. It just shows how the amplitude changes as we change the frequency of the driving force. When the frequency is the same as the natural frequency, then the amplitude is at its highest. Okay, on to new material. Waves. Waves are disturbances that carry energy but not matter. Again, matter travels a very little bit. It will oscillate about an equilibrium position, but it doesn't cover long distances with the waves. There's two types of waves. We have mechanical waves that require a medium to travel through, and electromagnetic waves that do not require a medium. In this course, we're going to be looking at mechanical waves. In electromagnetic waves, we have oscillating electric and magnetic fields, and you're going to look at this in more detail if you go on and do Physics 1b. Okay, waves are periodic disturbances. First of all, we're going to consider a pulse. In a lot of our derivations, we're going to be using a pulse just because it's simpler than a wave. So a pulse is not periodic. That's the only thing it does not share with a wave, but it's very similar to a wave. It's simpler to visualize, and so we will occasionally discuss pulses. A pulse carries energy, it has a height, it has a speed along the string, and generally it does not change its shape much as it travels along the string. So we've got two main types of waves: transverse waves, in which the direction of motion of the particles that makes up the wave is perpendicular to the direction of motion of the wave. So for example, a wave traveling along a string, or in electromagnetic waves, the electric and magnetic fields oscillate perpendicularly to the direction of travel of the wave. Okay, let's have a look at a transverse pulse now. What I've got here is a slinky coil. So the slinky coil is the medium, and in a second I'm going to send a transverse pulse along it. Okay, so hopefully you can see that the ribbon, which is tied to the slinky coil, is moving upwards and downwards, showing that the medium moves upwards and downwards as the transverse waves travels along the slinky coil. We also have longitudinal waves, in which the particles oscillate in the same direction as the waves travel. So for example, sound waves, or if we send a pulse along a spring, the bits which make up the spring oscillate in the same direction as the wave is travelling.
Okay, let's have a look at the longitudinal pulse now. So I'm going to use the same slinky and I'm going to send a longitudinal pulse along it. Pay careful attention to how the white ribbon moves as this longitudinal pulse travels along. Okay, so hopefully you can see that the white ribbon is moving forwards and backwards in the same direction as the pulse travels along the slinky coil.
So are there other kinds of waves? Well, yes, there are. Ocean waves deep out at sea have a combination of the particles moving in the same direction as the wave and perpendicularly. The water molecules actually move around in a circle as an ocean wave passes. So these aren't the only kinds of waves that we have.